Okay, so again, try to simplify this radical down into what they call simplest radical form, where you're taking basically every perfect square out of this thing, and you're breaking down as far as you can. I don't care which method you use. What I mean by methods, yesterday we had the perfect square chart, where you look for perfect squares that are in that. So you're searching, what number would go into 80 that's the biggest perfect square. Or for variables, you look for the biggest perfect square for variables. That's all fine and dandy. What I want to make sure of today is that, whatever method you choose, you're comfortable and you're good at it. You're quick. You don't have to put a lot of effort and time into it. Because if you're putting a lot of effort and time, that's just going to cause you a headache when you got 20 of them to do and you're still stressing about it. I want you to be able to do it quick. Now, I know yesterday I talked about variables. Certain variables, when you take them out of the radical, you're going to have an absolute value bar around them. The book will check that. I said I'm not worried about it. I'm not really worried about that, but I want you to know when you need to do it and when you don't have to do it. Because if you go to a college level math course, they will expect it. So it's good, it's a proper etiquette to try it so you know when to do it. So again, as you're doing this, hopefully you're kind of working on it here. Big thing, I'm going to use a lot of vocab that I used yesterday. So like the word radicand, radical sign, index number. If you're not comfortable with those, please ask when I'm using that word. We're going to try to do basic operations today. Obviously, we're going to do product rule, separating things. We're going to do quotient rule. Spend probably more time on that today than any. We'll talk about negative exponents, and not negative exponents, negative numbers, so we can get imaginaries. One of the things we do need to talk about today, that it's on the list for basic operations, when I use powers that are fractions. A lot of you said that you've seen that before. When we first started the laws of exponents, that's great, but we need to kind of review that. And conjugate rule. My goal today is get through conjugate rule. We gotta make sure that you know conjugate rules so you know how to rationalize things. A lot of you are still writing, which is fine. Keep going. Again, today I said you kind of want a calculator today in case you need to break down really kind of bigger numbers. I'm going to use bigger numbers today. Hopefully this kind of makes sense. Sure. It feels a lot smaller when I did this. I'm in pods.
Everybody's sitting in the back. Everybody sits in the back.
Yeah, it feels weird. It's like church. Everyone's sitting in the back.
You want me to sit up there?
No, it's fine. That'd just be weird. Let's stay in the back. Okay. Some of you might still be writing. Let's talk about the 80. How do you break up 80?
I did 8 and 10.
8 and 10. That's probably what I would have done too. 8 and 10 is easy. Other numbers you could have done, I think 5 and 16 or something like that. I've done that. But 8 and 10 is probably the one that I would do as well, just because it's kind of easy. Then the variables in the back, yeah, you can break them. Okay, so x, and then you got 5 y's, and this can get tedious. You get better at it where you don't have to do this, where you have to break up all these terms, especially for the variables. You get used to it, especially when I show you the shortcut later that you can do. When we get to the power rules, we're going to have the fractions and stuff. There's a shortcut for doing those. Maybe a shortcut, maybe keep doing it this way, I don't know. 8 and 10, then. How do we break those up?
2, 2, 2, and 2, and 5.
2 and 5. Good. Because this is breaking up the number 8. Breaking up the number 10 is 2 and 5. Just put up with this. Right there. Perfect. Thank you. And then the variables in the back. Now, I'm going to kind of cheat the system here. Let's just say that all these are down here. So, get the idea. All right. Now, what type of radical is it? What's my index number? 2. It's 2, right? The index number is the number on the outside of the little radical. It's the number out here. You got to know that number because it tells you how many you should circle. Is it a triplet? Is it a double? Is it a pair kind of thing? We are doing square root, so it is a 2. That's the only time in math you can assume it's a 2 when it's not printed. But then, so what we're looking for now is pairs. So hopefully you circle a pair of 2s, you circle a pair of 2s again. We got a pair of x's, pair of y's, pair of y's, pair of z's, and a pair of z's. So you circle everything that's in a pair. Then you kick them out. Cross one out, kick one out. It's basically, I should say the rule is, you cross all of them out that you've circled, and then you kick one of them out from each pair. That's basically how it works. I'll explain that rule here in a second. But so the 2's are on the outside. One of the x's on the outside, a y, and a z, and another z. So these are the items I'm kicking out. So I have 2 2's, an x, 2 y's, and 2 z's kicked out. Now what's left on the inside?
5 and a y.
5 and a y. Is the only thing that's left. You gotta leave them there. Don't lose track of things. They're the only things you didn't circle, basically. And then your final answer, you're going down to it, should be a 4, an x, y squared, z squared, and a 5y. Now, what we talked about yesterday is that one of the variables, I guess, it could be more than one, but in this case, there's one variable you're going to need absolute value bars. Which one is it?
X.
X. You got to guarantee that your variable is positive. The ones with squares on the outsides guarantee it, right? Because if you square something, the negative sign goes away. But since that x is by itself, you need to put absolute value bars. That's now I'm not going to really check that, but if you're checking the back of the book, they'll have an absolute value bar. They'll have the y squared and the z squared, and then the 5y's on the inside. You just leave that one. It doesn't matter what's inside the wrap. What matters is what's outside. I think with the rule I said yesterday is anytime you went from like an even power to an odd, that's the thing you have to check for. Questions, comments about any of the problems we've done, or I guess the problem that we've done, the problem. Do we feel comfortable with that? Okay. All right. Now, let's talk about doing the same style of problem. Well, let's do it for if we have a cube root. So, same thing, now I'm going to make it a cube root, so I'm going to put a little 3 here for the next number. They do have to print that if it's anything other than a square root. Let's go with 32, x, y to the 6, z to the, let's go to the second. Same exact idea. This would be probably one of the last ones I'll do for just product rule today, and I'll explain the concept why I keep using the product rule as my example. So the goal is to simplify this thing down. Now this is a cube root, so we're looking for triples. I'll give you a little bit of time here, and we'll move into fractions. We'll talk about that. Actually, possibly what I'll do is we might just show you the fraction rule right now, once we get going, how to deal with the exponents with their fractions, because that could help you simplify this maybe a little bit quicker sometimes. Okay, does anyone need more time? Looks like everyone's kind of getting wrapped up. Okay, 32. How do we break it up? 8 and 4 or?
5.
Okay, so, yeah. If you want the 8 and 4 route, and then we break down the variables, you're absolutely right. That when you break this down, you're going to break down the 8s and the 4s back into a bunch of 2s. We're just going to do that right away. So there is 3 2s there for the number 8. 2 times 2 times 2, that's 8. Then you have the 2 2s for the 4, so you write 5 2s. Now, variables, break them up, assemble them all up into individual variables. I'm going to show you that shortcut where you don't have to do this for variables. That's the thing I want to show you with the fraction rule. And the z's on the back. Now, the fraction rule, I typically only do the fraction rule with powers if you have a variable. I'll explain that here in a minute, because it helps you with this. You don't have to draw or write out like a ton of letters, especially if they have like powers of 14s and 15s. It's silly. Okay, now that we're here. Oop, almost got that thing all wrong. Now that we're here, what are we looking for?
Groups 3.
Groups of 3, triples. We're looking for 3s. It's a cube root. We're looking for 3 things to match. So that's the index number on the outside. So in this case, we do have a triplet of 2s. We have a triplet of y's. We have another triplet of y's. That's about it. Now it's the same rule as what I said earlier. You're going to cross them out, kick one out. Always just one. But you have to cross all of them out, the ones that you circled. So like on the 2's here, I'm getting rid of 2 of them, but one of them's leaving. I'm getting rid of 2 of them, getting rid of one of the y's. Getting rid of 2 of them, getting rid of one. It's always one leaves, the other ones go away that you've circled. So there's a 2, y, and a y on the outside. And then on the inside, we're left with 2 2's, an x, and 2 z's. Again, make sure that you have the cube root written down. Don't lose the power. I almost did that earlier. And now, finally, you can just combine things down. So the final answer on this one was that there's 2y squared. We have cube root. Was that 4xz squared? There you go. Now, if it's a cube root, and let's say one of the letters went to the outside by itself, just say one of them did. So maybe there was a w in here that had a power of 3. So you had a bunch of w's here. And you kicked one of them out because that was another triplet, but you only had to kick one out. So there's one sitting on the outside. You don't need to put absolute value bars in that one. The reason being is that the type of radical wasn't an even radical. It wasn't a square root or a fourth root. It was a third root, cube root. Cube roots, you don't need to put absolute value bars because it doesn't matter if it's positive or negative. Cube roots can actually have negative numbers. You don't need to guarantee the answer will be positive. So if you have a cube root or I guess any odd number, I guess, so multiples of 3, I should say, so 3, 6, you wouldn't necessarily have to make sure that that's positive. So just keep that in mind. It could be a negative number. Questions with this? Now, I did hint at that there is a shortcut for doing this problem. Well, what I consider a shortcut. Maybe it's not for some people. I'm going to write down the same problem again. X squared, x, y to the 6, z squared, and I'll keep the w to the third on it, just for right now, so you can. Okay. To change this so it has, instead of a radical, you're allowed to make this radical a power. And I think this is something I hinted at the very beginning of the year. You guys said you kind of recognize how to do it, you kind of remember it. You can change a radical to a power up here, but you make it a fraction. Now, how I know what the fraction is going to be on that parenthesis. It's the top number is going to be a 1. The bottom number is going to be whatever the index number was. So that's where this 3 comes from. It's the index number on that actual radical sign. And then the 32x, y to the 6, z squared, and a w to the third are inside. Does that make sense? This power rule for radicals. How many people have actually seen that before? Okay, so good. At least some of you have, or at least you remember it at least. Okay, you're allowed to do that in any type of radical. It could be a square root, fourth root, you just put a power of 4. Now, why that actually works is if you go back to exponential, equations kind of thing, a quadratic, when you take this power to the other side, power of 2, the inverse of it is actually a half. That's the inverse of it. It's the reciprocal, right? You flip it over. That's where it's actually coming from when you take it to the other side. Going half power instead of twice the power. And so that's where these these cube roots and other things come from, why they can be written as fractions. Now, why I say this is a shortcut. By doing your problem this method, I guess for the variables anyway, because it makes the letters a lot easier to deal with. All you have to do is the laws of exponents. You distribute the power through the parenthesis like a normal law of exponent problem, and it simplifies the variables for you automatically. It's kind of nice how it works. So if I distribute the power 32 to the third, now doing this part, that part, I wouldn't know how to do that. I don't have a shortcut for doing that. So my way of doing 32, and I know it's a cube root, I would do it the old school way where you break it up into a bunch of 2's. And just do it the old school where you kick some out, where you know it's a third root. So for numbers, this isn't the best way to do it. So like off to the side, I'd have to do this like over there. But for the variables, it makes a ton of sense. That it's going to be x to the third, because I'm just multiplying the power on there. Y, and now I'm taking 6 times a third, so it's 6 over 1/3, because when you actually multiply a number times a fraction, the number goes to the top of the fraction. Z to the 2/3, because you're going to actually take 2 times 1/3, the 2 multiplies to the top. That's how fractions and numbers work. And then W to the 3/3, because again, the number multiplies on the top of the fraction. And now you can start to see why this is actually easy to deal with, because it will actually simplify. What is 6 over 3? That's a 2, right? So this turns out to be y squared, just a 2. 6 divided by 3 is 2. W to the 3 over 3, what's 3 divided by 3? 1, right? So W to the first. Do these have fractions on it anymore? No, so there's no radical around them. Those are outside the radical now. Z to the 2/3, there's no way I can simplify 2/3. I can't simplify that. I can't divide 2 divided by 3, it's a weird decimal. X to the 1/3, I can't do anything with that. So that's still a fraction. And then up here, yeah, I just kick out the 2's. I would do this one like the old school way where I kick out 2's, where it's, it's 2 and a cube root of 4 on the inside, that type of thing. So that's how I deal with the 32. But now you can see what your final answer is, because anything that has fractions are still under the radical sign. So like this x is to the first power and it's still in a radical. This z is to the second power, it's still in a radical. And then anything that doesn't have powers, like that, or fractions, those are on the outside. So there's going to be a 2, there's going to be a y squared, and a w to the first. And that's exactly the same answer we said earlier. Makes sense? Like how I said it was like, it's simple if you can do it with the fraction rule. And it actually makes variables way easier to deal with. You don't have to separate them like into the hundreds of variables. You can actually just do it with fractions really quick. Now, one of the questions I get is, people try this. They start doing this with the fraction rule because they like that. They don't like it for the numbers because that's just awkward. You just do it the old school way. But for variables, it makes sense. But the question I always get is, how do you do it when you have it, let's say it's a square root. So you're doing, some type of square root. I don't care what the number is, but it's, like x to the 5th. You're doing a square root of it. How do you do it with the shortcut? Okay, what's the index number? 2. Okay, so it's x to the 5th over 2, right? Because the fraction's a half. So if you don't like writing like that, you can write like this. X to the 5th all to the half. You can write like that, it's the same thing. But you'd have to distribute the power in, you have to multiply the power on the 5, which is this. And how do you simplify it? Well, this is what you do. This is the same thing. You're allowed to separate these into individual items. So, because anytime you separate a bunch of x's, you would add them together. So 5 halves, what that is that's x to the 2 over 2, x to the 2 over 2, and x to the 1/2. Because anytime you multiply a bunch of bases together, right, a bunch of bases, you'd add the powers. Well, when you add fractions, you only add the top numbers. The bottom number stays the same. So the bottom numbers are 2. So all I had to make sure of is when I'm doing this, make sure the bottoms are 2's, because that's the fraction I have, it has 2 on the bottom. And just make sure the top numbers add up to be 5. And how do I know what to make them? Is I just make them whatever the bottom number is, I just break them up into that many items. So 2 over 2, 2 over 2, 1 over 2. So I don't try to go over whatever the bottom number is. So if the bottom number is 4, fine, I go 4 over 4 and 1 over 4 to make 5. That kind of thing. But whatever these are, these simplify to be 1s. So this is x to the first, this is x to the first. Those don't have fractions, so they're not in the radical anymore. But this one is. So the final answer is that there's 2 x's on the outside, and on the inside there's 1x. I had one that still had a fraction on it. That's the shortcut that you can do for variables. Now you get used to it because here's the idea. Instead of doing this, because I know you're thinking, well, that isn't any simpler, right? That took actual effort. There's the shortcut you can do is, since you have 5 halves, what is 5 divided by 2? 2.5, right? So it's x to the 2.5. Well, that's written as this. Okay, that's 2.5, right? That's what 5 divided by 2 is. That means you have x squared, x to the half. That you separate, just make them their own x's. 2.5. So you can just divide, whatever top divided by bottom is, now you know instantly what the answer is going to be. X squared and whatever the fraction is behind it. Questions, comments about how to use the fraction rule to help you out to make this easier? Now, some of you might not choose to do that. That's fine, you don't have to. I'm just giving you that option that maybe that's faster for you. Maybe that makes a lot of sense, like, oh man, I can do that way quicker than separate and circle and kick out. Okay, let's move on, let's do fraction rules. This is one of the things I wanted to talk about yesterday. I think it was one of the problems that I hinted at that I wanted to go through. All right, I'm just going to start with something simple. Square root 2/3. Yeah, I'd just like to write that down. We're going to start simple and work our way up. Start with 2/3. No variables yet, nothing like that. Now, the quotient rule that we had yesterday, the quotient rule said that if you have a fraction that you cannot simplify, you'd have to separate it into its own radicals. So you can separate the top versus bottom. Or if you had one that was separate, you could put it back to 1. That's called the quotient rule. As long as you have the same radical, you're allowed to do that. Now that we have it separated, the rule is you just need to really get rid of the radical off the bottom of the fraction. So it's called rationalizing. You can never have a radical on the bottom. So the rule is you multiply by pretty much whatever the bottom is. So that's the shortcut for how you can do it. Now there's other ways. What I would do if this number is really big, separate it. Separate the bottom number and then figure out what you need to multiply, like the bare minimum you need to multiply to make sure that all the pairs can cross out, because you use square roots. So I need to make sure there's a bunch of pairs. So really, since there's only one number on the bottom, I only have to multiply it by a 3. But if I multiply by a 3 on the bottom, I have to multiply by a 3 on the top as well. Here's why. You're actually multiplying by the number 1. Root 3 over root 3 is the number 1. So this is called a multiplicative identity, that if you multiply by 1, it doesn't actually change your answer. So that's what I'm choosing to do. This is just the number 1. Now, why I'm picking 1 is because it will simplify the bottom. So on the bottom, when you actually multiply straight across, because that's how you multiply fractions, you multiply straight across, I'm going to get a root 6 on the top, and on the bottom, I'm going to get a root 9. Now, if you don't want to multiply them together, you don't have to. You can just put the two numbers side by side, circle pairs, kick them out. You don't actually have to go back to the original number. But what's the square root of 9? 3. And you have a root 6 on the top, that's your answer. Like, that's simplified. Don't try to take 6 divided by 3. Don't do it. You're going to go right back to what you started with. The 6 is in the radical, so you're not allowed to do that anyway. Now, if this number on the top can break down, fine, break it down later. Question?
Could you start by taking that radical and putting it into exponent form?
Say it again? Oh, like
2/3 to the 1/2 power.
Yeah, you could do that way too. So you could do it would work all the same. Yep. Now, I was hinting at something earlier where I said if there's like a bare minimum of things you can multiply by. Like on this one, I had to multiply by the 3. It made a 9 perfectly at the bottom, took the square root, fine, it was done. It was easy to do, okay? But if the number was something like the number 12 on the bottom, so let's say this is root 5 over 12. Okay, you separate, you know, because I can't actually divide those. 5 is unique to 12. So 5 and you have a 12. The idea is that I don't have to multiply by another 12. I don't have to. Because 12 can actually simplify a little bit. So there's a bare minimum of things I need to actually multiply by. So how I know is what I would do is I would separate the 12, like to begin with, like this. That's a 2, 2, and a 3. That's what 12 is. It's 4 times 3. So I need to make pairs, right? Because this is a square root. So what do I need to multiply on the bottom to guarantee that I have at least a couple pairs? What's the minimum number I need to multiply by? 3. I need to put a 3 on the bottom. Because right now I already have a pair of 2s, so I'm going to circle and kick one out. But the only thing I need to really combine on the bottom is I need another 3. I need another 3 on the bottom. That will make 2 of them so I can have a pair. And I can kick them out. So if I do this, the top is going to turn out to be 15. The bottom is going to have a couple 2s and a couple 3s now, because you just multiply straight across. And you can put them all into one. That's the proper rule. You can put them back into one radical. So now I'm going to have a couple pairs of 2s and a couple 3s. Those would go outside the parenthesis. So it looks like I'd be moving a 3 out and a 2 out, so that I'm going to have a 6 on the outside. There's nothing left in the radical. And that would be the final answer, because 15 doesn't break down at the top. There's no pairs in it. Do you see, like, you don't have to multiply by 12? You can. Don't get me wrong. You can multiply by 12, you can multiply the top by 12, but that means you're going to have to simplify. That'll take more steps than just trying to figure out what's the bare minimum of things I need to put on the bottom to make guarantee that there's pairs or triplets, or whatever I need. Because I can do the same process for if I wanted to do a cube root. I can do the exact same stuff. So if I'm doing that same problem I just gave you, it was a 5 over 12. But now I'm going to make it a cube root. Now you got to multiply by different things. Instead of multiplying by whatever the bottom is, you got to guarantee that you're going to get a triple on the bottom. So the top doesn't look like I'm going to do anything on the top right now. But the bottom is a 2, 2, and a 3, right? So the things I need to add on the bottom to make sure that I can guarantee that there's no radical left. It looks like I'm going to have to put another 2 on the bottom, because I need 3 of them, and I need 2 more 3s. I'm going to have to put that on the bottom to guarantee that I'm going to get 3 of those items on the bottom so I can kick them out. Does that make sense why I'm multiplying by that? Guarantees I'm going to get, 3 of each item that I have. This is the original problem. So now when you combine, I'm going to have a couple 2s, or 3 2s, I'm going to have 3 3s, so it's perfect so I can kick them out. On the top, it looks like I'm going to get 90 on the top. It's 5 times 2 times 3 times 3, but on the bottom, I'm going to have a couple 2s and a couple 3s, so I'm going to have that 6 still on the bottom. Because if I circle them, 1 goes out, 2 goes out, and a 3 goes out, I should say. 1 of each. Questions on the simplifying parts? Okay. We didn't get to the cont'd rule today. That's fine. We'll finish it tomorrow. Same kind of style tomorrow. I'll kind of pick and probably pause again tomorrow. We'll try out a couple problems. I probably will just jump right into conjugate rule. I'm not going to probably review some of the stuff we've done today. I think it's kind of straightforward. But we have to do imaginary numbers. And we have to make sure that we kind of know how to add and subtract radicals tomorrow. So we have kind of another 12 docket. Tomorrow we probably will get our next assignment for the week. So it'll be probably the last assignment for the week. Okay, but yeah, come on.
That's okay. I know you're still. It makes sense. Yep. I did. Yeah, I better make that.